All right, so today we're going to look at the 2009 AP exam question number 5. And you see we have reactions X, Y, and Z with some thermodynamic data here, delta H, delta S, delta G. We've seen a couple of these before. You know, if they give us reaction X, reaction Y, and then you see reaction Z here, is a combination of X and Y. And we're going to want to know some or figure out some information about reaction Z here. So you can see if I add reaction X with reaction Y, I can get Z, as long as X and Y are flipped. Okay, so I need 2 carbon monoxides, and I see 2 carbon monoxides here. 1 solid carbon, 1 solid carbon, 1 carbon dioxide gas, 1 carbon dioxide gas. And you can see that hydrogens will cancel out, as will waters. So you should notice that, hopefully, that, okay, I can get Z by adding X and Y and flipping it. All right, now what we also need to do is remember, what does delta H, delta S, and delta G tell us when we see this information? And I had you work on this through the year. Delta H tells us how much energy is going into or coming out of a reaction. Is it exothermic or endothermic? Delta S tells us whether or not the entropy of a reaction is increasing or decreasing. And then delta G tells us, is the reaction thermodynamically favored as written? Positive, no. Negative, yes. So that's hopefully some stuff that's bubbling through your head as you get ready to go. Now it's a multi-step question, so again, grab as many of these points as you can. First up, for reaction X, we want the expression for the equilibrium constant, Kp. Now since it says Kp, try to use pressures. If you used brackets, it probably wouldn't be the end of the world. You'd probably still get the point, but when it says Kp, we're going to look at our reaction X, products over reactants, and again, we only want the gases. Sorry, carbon, you're not invited. So that will be our Kp expression. If they had said reaction Z, okay, again, carbon wouldn't be in it, and it would be the pressure of carbon dioxide over the pressure of carbon monoxide, but we'd have to square it because of the the coefficient of 2. So just in case you see the pressures are treated just like concentrations in brackets. You got to raise them to the power of the coefficient in the reaction. All right. Also for reaction X, will the equilibrium constant increase, decrease, or remain the same if the temperature goes up? So if we add heat to this reaction, well, delta H is positive 131 kilojoules per mole. That means we have an endothermic reaction. If I have an endothermic reaction, that means heat is on the reactant side. It's treated as a reactant. So if I add heat, poke the heat, I'm going to make the reaction go that way. I'm going to form more products. More products will make in the numerator of my Kp expression will mean my K value is going to increase. All right, so it is endothermic. So adding heat causes a shift towards product, increasing product concentration, or you could say increasing product pressures. And that will increase my Kp value. Now, you could also, through some magic of manipulating equations, you're going to have the delta G equals negative RT ln K equation in your test-taking packet. So you could do something that shows that, as you see here, that when temperature is increased for a positive delta H in endothermic reaction, the natural log of K and therefore K also increase. That seems like a trickier way for me. I'm a simple folk. I want to poke. So if you can just poke a reaction and see which way it's going to go, that would probably be my personal best bet. Now, for reaction Y, is the value of Kp greater than 1, less than 1, or equal to 1? So now we're looking at reaction Y. And when I look at reaction Y, Carbon monoxide plus hydrogen makes carbon monoxide and water. They're all gases, they're equimolar. Oh my gosh, what am I going to do? How am I going to plug? Stop. Collaborate and listen. What does delta G tell me? Delta G tells me, is this a thermodynamically favored reaction as written? Positive delta G? No, it is not. And so that means there's going to be more reactants than products. So therefore, we will have a Kp less than 1. Again, you could play the reaction game that delta G equals negative RT natural log of K. So if I take negative RT, I'm going to have to multiply that by a negative number, ln Kp, in order to get a positive delta G. So if ln Kp is negative, that only happens when Kp is less than 1. Again, if that floats your boat, fantastic, but we practice so often remembering what delta H, delta S, and delta G means, what it tells us. Delta G, not thermodynamically favored, will have a K less than 1. If delta G is negative, it is thermodynamically favored, we would have a K greater than 1. All right, so again, for reaction Y, which is larger, total bond energy of reactants or total bond energy of products? All right, I see bond energies and I see reactants, bond energy, products. That brings us back to good old delta H. And remember, when we do delta H with bond energies, it's broken minus formed. We break them in the reactants and we form them in our products. And if you look back on our data table, my delta H for reaction Y is a positive value. It's endothermic. So when my delta H is positive, that means my broken has to be greater than my formed. So my reactant bond energy will be greater than my product's bond energy. All right, so that's the explanation, and there it is kind of written out for you. It's probably a good idea to let them know that you recognize that the delta H value comes from broken bonds minus formed bonds when it comes to bond energy. It's tricky because when we use delta H tables, it's products minus reactants, but when we do bond energies, reactants minus products. Got to remember that. All right, next up, true or false. On the basis of the data in the table, it can be predicted that reaction Y will occur more rapidly than reaction X. Again, my data, delta H, delta S, delta G. Delta H is energy, delta S is entropy, delta G thermodynamically favored or not. Nowhere in my data does it help me explain how fast a reaction goes. Okay, again, nuclear decay reactions all are thermodynamically favored. Some take a millisecond, some take billions of years. They will have negative delta G values though. Reaction rate data tells us about how fast a reaction will go. All right, now our last part, getting to reaction Z. Okay, so now we do need to recognize that we got reaction Z by adding X and Y together when they were both flipped. Okay, so our first part is delta S for reaction Z. Again, all of these questions here, part 1, 2, 3, are for reaction Z. Is delta S going to be positive, negative, or 0? Okay, again, the trump card for delta S predicting is moles of gas. And so when I look, I have 2 moles of gas on my reactant side, carbon's a solid, 1 mole of gas on my products. Less moles of gas is definitely going to be a decrease in entropy. Okay, 2 moles of gas are forming 1 mole of gas. And you could mention the 1 mole of solid, that's okay. All right, so when you're losing moles of gas, you're definitely decreasing your entropy. The other thing you could do is you could use the numbers. when you add the reverses, so negative 134 and negative 42, you get negative 176. And there you go. That's your sign for your delta S. You did not have to do that. You could simply state that there's less gas. Now for part 2, determine the value of delta H. Well, now you're going to have to simply do the addition. So again, the reactions were flipped, so negative 131, negative 41. So when you add them together, you're going to get negative 172 kilojoules per mole. Okay, or you could write like they have up in the data table, kilojoules per, or kilojoules moles to the negative 1 power. Please make sure you label those answers. Okay, the labels are given to you, so just make sure you're using the right ones. Last part. A sealed glass reaction vessel contains only carbon monoxide and a small amount of carbon. Okay, again, we're dealing with my reaction Z. So the vessel has some carbon monoxide and a tiny bit of carbon. The reaction occurs, temperature is held constant. Is the pressure going to increase, decrease, or stay the same? And explain. Okay, so again, here's my reaction. And as the reaction goes, again, I go from 2 moles of gas down to just 1 mole of gas. So there's less gas. What causes gas pressure? Collisions. Collisions between the particles and the container walls. So if there's less gas particles, there's going to be less collisions, which means there's going to be less pressure. Okay, stick to your basics, stick to your guts. You know pressure is caused from particle collisions. More particles, more pressure. Less particles, less pressure. Temperature affects this as well, so does volume, but again, we were in a sealed container at a constant temperature. All right, I hope this helps you out, and I'll see you soon.